Hello everyone. In this video, I'm going to talk a little about Kirchhoff's rules, and hopefully that'll help you get through Lab 4 and the write-up. To start with, I want to talk about resistors in combination. You'll find that this is actually pretty similar to the capacitors in combination that you've been learning in lecture. When you connect resistors end to end, and there are no other connections between those two ends, we call this a series connection. The same thing as with capacitors. When you have resistors connected in series, such as R1, R2, and R3 here, you can reduce those resistors to one single resistor that has an equivalent resistance. The formula for the equivalent resistance is shown right here. Basically, you just add together the individual resistances of the resistors. Note that this is the opposite of what is true for capacitors. For capacitors, if they are connected in parallel, we can add together the capacitance. And also note that when you have resistors connected in series, all of those resistors have the same current running through them. So this can sometimes help you to identify whether two resistors are connected in series with each other. When you connect the resistors by their ends, again with no other connections in between, we call this a parallel connection. This is also true with capacitors. Resistors that are connected in parallel, such as R1, R2, and R3, can be reduced to one equivalent resistor. The formula for the equivalent resistance is shown near the bottom. Here you're adding the inverses of the resistances, 1 over R1 plus 1 over R2, etc., and the result is 1 over the equivalent resistance. Note again that this is the opposite of what happens with capacitors. For capacitors connected in series, we add the inverses of the capacitances. And also note that when you connect resistors in parallel, they have the same potential difference across them. So for example, if the potential difference across resistor 1 was 10 volts, then that would also be true for resistor 2 and resistor 3. Here's a quick example about resistors in combination. So our circuit is shown in the top right, and we are asked to find the equivalent resistance between points A and B, and we're asked to calculate the current in each resistor. We start by identifying which of these resistors are in series or parallel with each other. Looking at the 4 and 7 ohm resistors, for instance, we can see that they're not in series with each other because there's this junction that's connected to the 10 ohm resistor. And the same is true for 9. This is not in series with anything right now. The 7 and the 10 ohm resistor, on the other hand, are connected in parallel with each other because the two ends are connected. So the first thing that we will do is combine the 7 and the 10 ohm resistor, labeling that combined resistor as R710, and using the formula from the previous slide, we find that the equivalent resistance of those two resistors is 4.12 ohms. So we've taken this 7 and 10 ohm resistor, and we've effectively combined it into a single resistor that has a resistance of 4.12 ohms. Now you have three resistors in series with each other, and you can easily combine these by just adding together the resistances. The equation from the previous slide gives us 17.12 ohms. So now we've taken these three series resistors, and we've reduced them to a single resistor that has an equivalent resistance of 17.12 ohms. We've reduced our entire circuit down to one resistor that has an equivalent resistance of 17.12 ohms, and this answers part A. For part B, we are asked to apply a potential difference of 34 volts between points A and point B, so we can imagine that there's just a battery connecting them. And we will use that reduced circuit that we found on the previous slide. So this circuit at the bottom is the one that we're actually going to be working with. at least to start. Now we can use Ohm's law to find the current that's running through this circuit at the bottom. Ohm's law says that V is equal to I times R. The potential difference across this resistor is 34 volts because that's what we've applied. We know what the equivalent resistance is, so all we have to do is solve for the current, and we'll find that there's a current of 1.99 amps flowing through this entire circuit. Note that this circuit is one branch. There's no junctions for the current to split off. That means throughout this entire circuit, you have 1.99 amps of current flowing. Now we will move up one diagram. In this diagram where we have 3 resistors with R710 in the middle, we still have 1.99 amps of current flowing through this entire circuit because, again, there's no junctions for that current to break off. This means that through resistors 4 and 9 in particular, we have 1.99 amps of current flowing through. And now when we move up to the top diagram, our original circuit, we have 1.99 amps of current flowing through the 4, the 9 ohm resistors, and also this battery that we've put in. But this R710 resistor is split into 2 parallel resistors. Now the R710 resistor in the middle figure does have 1.99 amps of current flowing through it in total. However, when the current gets to this junction right here, it has to split. Some of that current will go up and some of it will go down. In total, though, there will be 1.99 amps running through the 7 and the 10 resistor. But individually, those resistors will see somewhat less of that current. To find the current that each of those parallel resistors sees, we want to actually apply Ohm's law to that R710 resistor. So what we're looking for in particular is the voltage drop across that parallel combination. So we want to use V is equal to I times R. I will be the total current going through the R710 resistor, and R710 is the resistance of that resistor. We find that the potential drop across the R710 resistor is 8.2 volts. This is also going to be the potential drop across the 7 and the 10 ohm resistors. And so finally, to find the current going through the 7 ohm resistor, we use Ohm's law with that potential difference that we just found, and we'll see that there is a current of 1.17 amps flowing through the 7 ohm resistor. And we do the same for the 10 ohm resistor, and we'll find a current of 0.82 amps. So notice that if you add together the total current flowing through the 7 and the 10 ohm resistors, you do get that 1.99 amps that's flowing through the rest of the circuit. And also note that the path that has more resistance, the 10 ohm path, sees less current. So more current flows through the path of least resistance. We'll talk more about that later. We can analyze most simple circuits using this method of Ohm's law and combining the series and the parallel resistors. And it may seem a bit circular logically, but this is basically what I would define a simple circuit as. There are more complex circuits, though, where we can't combine the circuit elements because basically they're not in series or parallel with each other. For example, in this circuit shown at the bottom, if you were to look at, say, resistors with 6 and 3 ohms, you might think that they're in series with each other, but there's this junction B, and that junction's connected to this third resistor that prevents them from being in the series with each other. Also, you may think that they look like they're in parallel with each other because the ends are connected, But on the top side here, there's a battery that's between those two ends. So again, they're not in parallel with each other, and we really can't reduce them to anything simpler. To analyze these circuits, we have to use Kirchhoff's rule. By the way, Gustav Kirchhoff was a German physicist in the 1800s, and you'll find that pretty much everybody pronounces his name differently. Sometimes you'll hear Kirchhoff or Kirchhoff or Kirchhoff. I'm going to stick with Kirchhoff, but know that I have actually no idea how to properly pronounce his name. And the internet itself can't seem to come to a consensus on this either, so I'm just going to stick with Kirchhoff. So there are two rules or laws that we have to follow. The first one is called the junction rule. This says that the sum of the currents entering any junction must equal the sum of the currents leaving that junction. If you look to the circuit at the bottom, you'll see that we labeled the current traveling through the right branch as I1, the current traveling down the middle branch as I2, and the current in the leftmost branch as I3. So then the junction rule, we would apply it to a junction. In this example, we'll pick junction B. And the junction rule says that the junction or the current going into junction B is I1 plus I2. And this has to equal the current that's leaving the junction. So that's I3. So the junction rule applied to junction point B says that I1 plus I2 has to equal I3. The second rule is called the loop rule, and this rule says that the sum of the potential differences across all the elements around any closed circuit loop must be zero. We'll go into more details about both rules in the next few slides, but just real quick to apply it here, what we want to do is pick a starting point for our loop. We want to pick a route that the loop will travel. So in this example, I'm going to pick the outside of the circuit. And then I'm going to walk around that loop and see what happens to the electric potential as I walk around. So starting at A, the first thing I do is cross over a battery. This is going to increase my potential by 24 volts. When I walk across this resistor, I'm going to decrease my potential by delta V1. And then using Ohm's law, we can write I1 R1. As I continue walking along this loop, nothing happens as I walk along the wires, but when I get to this resistor on the left side, I again decrease potential. So then here I would be decreasing by delta V3. And using Ohm's law, I could write that as I3 times R, or I3 times R3 as I have written here. And then finally, I'm going to cross this battery, and that's going to increase my potential by epsilon. After that, I get back to the point I started with, and the loop rule says that all of those voltage differences that we just found have to equal 0 once we get back to where we started. The junction rule is basically just conservation of charge. In this figure on the right, you have current I1 going into a junction, and this has to equal I2 plus I3 that's flowing out of the junction. So you have charge traveling in on this current, and some of the charge goes up, some goes down, but the total charge has to stay the same. So the junction rule ends up just being conservation of charge, which you could state as the total charge never changes for an isolated object. And for our purposes, we can just think of this as saying that electrons are not created and electrons are not destroyed inside of a circuit. So let me also mention that electrons typically travel in the opposite direction of the current arrows that we typically draw. because the current arrows indicate the direction of positive charge and electrons are negative charges. But nevertheless, hopefully this makes intuitive sense. If you have an electron traveling along a circuit and it gets to a junction point, that electron has to choose whether to go left or right. It can't just stay at the junction because charge is not allowed to build up at a junction. And essentially this means that electrons are just very decisive. They always decide whether they should go one way or the other way. Now you may have heard this saying before, that current always travels the path of least resistance. This is not entirely true. Technically speaking, you should say that more current travels the path of least resistance. As we saw in the previous example, both the 7 and the 10 ohm resistors both had current traveling through them. It's just that there was more current traveling through the 7 ohm resistor. Physically, you could say this is because the electrons will want to go down the 7 ohm path, but eventually there's going to be so many electrons on that 7 ohm path that some of them might find it easier to go the 10 ohm way. So for example, if you've ever been driving on the highway and there was maybe a small accident ahead of you on the highway, when traffic starts to back up, you may want to take the nearest off-ramp and skip over that accident. This works perfectly well until everyone takes the off-ramp, and then the off-ramp is even more backed up than the highway. In that case, you may want to just stick on the highway. Okay, it's not a perfect example, but hopefully it gives you the idea. The loop rule you can think of as being related to conservation of energy. So if a charge is forced to go around a closed loop, then it has to have the same energy that it started with when it gets back to its starting point. So if you have a charge that starts at A, it increases its potential as it goes across the 24-volt battery, then it decreases its potential across both of the resistors along the outside of this path, and then finally it increases its potential across that second battery. It has to have the same energy when it starts at point A as when it gets back to point A. Another not necessarily perfect mechanical analogy comes with a comparison to gravity. When you throw a ball upwards, the potential energy of that ball increases until it gets to the top, and then that potential energy decreases again as it comes back down. And when it gets back to your hand, it has the same potential as when it started. And then the last thing I'm going to go over in this video are the rules for using Kirchhoff's rules. The very first thing you have to do is guess a direction for the current in each branch of the circuit. You should make guesses that make sense, but you don't have to worry about whether your guesses are right or wrong, because at the end, if you guessed wrong, you'll just get a negative number for the current. So for example, in the circuit at the bottom, we might guess that the current traveling in the right branch is going to the right and down, so clockwise through this branch. Right, this makes sense because the battery with the positive terminal on the right side should be driving current clockwise along this loop. We'll label the current in that rightmost branch as I1. The second battery on the left should also be driving the current clockwise around that left loop, and we will label this as I3. The middle branch is less obvious because we have two competing currents. You have the 24-volt battery is trying to drive current upward, and the epsilon battery is trying to drive current downward. So we don't really know, or we should say it's not necessarily obvious, whether the current is going up or down in that middle branch. Just to make a guess, we'll say it's going down, and we'll label this current as I2. If you follow along with the example on the next couple slides, you'll see that guessing I2 downward is actually wrong. But that's okay because we just get a minus sign for the answer, and that tells us that the current is actually traveling upward. And the second step is to choose loops for us to walk around. Note that this is completely unrelated to the direction of the current that we just chose. How you choose these loops kind of just depends on what you're looking for. You could choose a loop around the entire outside like we did previously, but in the next example, what I do is actually I choose a loop that starts at A and travels clockwise along the small loop on the right, and then I choose a second loop that starts at B and travels counterclockwise along the loop on the left. So you really do have a lot of freedom in how you choose these loops, both the path and the direction of the loops. And as long as you follow the rules, you don't have to worry about the direction or which loops you chose. You'll always end up at the right answer. The rules for the changes in voltage as you walk along these loops are summarized on the right side of this slide. Basically, this just tells you whether you use a plus or a minus sign in the loop rule equation. So in all of these examples, we are walking along the path starting at point A and we're walking to point B. In example A, as we walk to the right, we cross over a resistor, and we're crossing that resistor in the same direction that we chose the current. In this case, we want the change in potential to be negative, so we'll use minus I times R in our loop rule equation. In example B, we're again walking to the right, but when we walk across that resistor, we're walking in the opposite direction that we chose the current. So when we walk across a resistor in the opposite direction that we choose the current, we want to use a plus sign in our loop rule equation for the change in voltage. And then batteries are easy. In example C, as you walk to the right, you're walking from the negative to the positive terminal. In that case, you want the change in voltage to be positive, so you use a plus sign. And then finally, in example D, you walk to the right and you walk from the positive to the negative terminal. So then you want the change in voltage to be negative, and you use a minus sign in the loop rule equation. So, for example, applying the loop rule to the blue loop that I've drawn, we start at point A. The first thing we do is we walk from the negative to the positive terminal of a battery. So then we're increasing our potential by 24 volts. Then when I walk along the wire, nothing happens. I cross over a resistor in the same direction that I've chosen the current. So I'm going to decrease potential by minus I1 times R, which will be 6 ohms in this case. I continue walking along the wire, nothing happens. Then I go up that middle branch and I walk across a resistor in the opposite direction that I've chosen the current. So according to example B, that means I should use plus I2 times R2, or 3 ohms in this case. After that, I get back to point A where I started, so that is going to be equal to 0. So applying the loop rule to the blue loop gives me one equation. If I apply the loop rule to the green loop, then I'll get another equation, and I will get a third equation from the junction rule. So then at the end, I have a system of independent equations, and then I have to simultaneously solve this system of equations. At the end of the day, you will have the currents traveling through each branch of the circuit. You'll have any resistances that aren't given to you, for example, this R on the left. And you'll have also any voltages that aren't given to you, this epsilon, for example. That's what happens in the example that I have in detail on the next few slides. I don't intend on going over this example in the video because you're also going to learn about this in class, but the example is here for you to work through, and hopefully this gives you enough details to get through Lab 4 and the write-up. And of course, if you have any questions, please let me know. Good luck!